In this video, we are going to discuss questions based on calculating potential energy of a system. So let's start with the first question. What is the potential energy of an electron and proton in an hydrogen atom if the distance between them is 5.3 times 10 to the power negative 11 meter? So here you have an electron and a proton, and we know that charge on electron QE is negative E, whereas charge on proton, which I will write as Qp, is positive E, where E is the elementary charge that has value 1.602 times 10 to the power negative 19 Coulomb. The distance between them will be given as R, 5.3 times 10 to the power negative 11 meter, and I need to find what is their potential energy. So potential energy U is given as K Q1 Q2 over R, where Q1 and Q2 are the two charge object. In our case, it is electron and proton here. So I can write this as K, charge of electron to be negative E, charge of proton to be positive E over R. That gives me negative K E squared over R. Now let's substitute. U will be equal to negative 9 times 10 to the power 9. E is 1.602 times 10 to the power negative 19 squared over the distance between them, which is 5.3 times 10 to the power negative 11. And when you solve this, you get the potential energy between the two charge particles to be equal to negative 4.36 times 10 to the power negative 18 joule. Next problem. What is the potential energy of two charges of 4.2 microcoulomb and positive 6.1 microcoulomb, which are separated by a distance of 50 centimeter? So here you have charge Q1 equals positive 4.2 microcoulomb. Micro means I have to multiply this with 10 to the power negative 6 coulomb. Q2 will be 6.1 microcoulomb, which is 6.1 times 10 to the power negative 6 coulomb. And the distance between them is 50 centimeter, which is equal to 0.50 meter. And I need to find the potential energy of the two charges. So again, we can write potential energy U to be equal to K Q1 Q2 over R, which is 9 times 10 to the power 9. Q1 is 4.2 times 10 to the power negative 6. Q2 is 6.1 times 10 to the power negative 6 over R, which is 0.5. And when you solve this, you get potential energy U to be equal to 0.46 joule. What is the potential energy of three charges of 2 microcoulomb, negative 4.5 microcoulomb, and negative 3.4 microcoulomb that are in a straight line with negative 4.5 microcoulomb charge in the middle, and each charge is 5 centimeter away from its adjacent charge? So here in this question, you have been given three charges, which I will write as Q1 equals 2 microcoulomb. So micro we can write as 2.0 times 10 to the power negative 6 coulomb. Then Q2 is negative 4.5 microcoulomb. So again 10 to the power negative 6 coulomb. And Q3 as negative 3.4 microcoulomb. So 10 to the power negative 6 coulomb. And they are placed in a straight line. So I will call Q1, Q2, and Q3. And the distance between each of the adjacent charge is 5 centimeter. And the charge Q2 is at the center. So we can write the distances between these charges first before we begin solving. As you can see from the figure, I will call distance between Q1 and Q2 as R12. And this distance R12 is equal to 5 centimeter, which is 0.05 meter. Then between Q2 and Q3 as R23, and this distance R23 is also 5 centimeter, which is 0.05 meter. And the distance between Q1 and Q3 as R13, and R13 from the figure is 5 plus 5, which is 10 centimeter, that is 0.10 meter. Now to find the potential energy of the system, we are going to calculate the work done in bringing each of these charges in their respective position. So let us first start with charge Q1. When I bring Q1 to its position in the beginning, there are no other charge for Q1 to interact with. So work done in bringing Q1 from infinity to its position over here will be equal to 0, as there is no charge present for Q1 to interact with, and we have to do no work to bring it from infinity to its position. Then we bring charge Q2. While we bring Q2 to its position, there is charge Q1 already present, and Q2 will interact with Q1. And because of their interaction, we have to do work against Q1 to place Q2 in its position. So work done in bringing charge Q2 can be written as W2, which will be equal to K Q1 Q2 over R12. So we solve for this. K is 9 times 10 to the power 9. Q1 is 2 times 10 to the power negative 6. Q2 is negative 4.5 times 10 to the power negative 6. And distance between them is 0.05. That gives me work done in bringing charge 2 to be equal to negative 1.62 joule. Now we do the same thing for charge 3. When you bring charge Q3, Q1 and Q2 are already present here, and Q3 interacts with them. And because of this interaction, we have to do work against Q1 and Q2 to place Q3 in its position. So work done in bringing charge 3 can be written as K Q1 Q3 over R13 plus K Q2 Q3 over R23. Now K and Q3 are common, we can take it out, and we write this as Q1 over R13 plus Q2 over R23. Now substitute. W3 will be equal to 9 times 10 to the power 9. Q3 is negative 3.4 microcoulomb. Both Q1 and Q2 are measured in microcoulomb, so we can take their power common outside. Q1 is 2, and the distance between 1 and 3 is 0.1. Q2 is negative 4.5, and distance between 2 and 3 is 0.05. And when you solve this, you get work done to bring charge 3 to be equal to 2.14 joule. Now this work done in bringing each of these individual charges is stored as the potential energy of the system. So I can find the final potential energy U by adding the work done in bringing individual charges. So U will be equal to W1 plus W2 plus W3, which is equal to 0 minus 1.62 plus 2.14. That gives me potential energy of the system to be equal to 0.522 joule.